All right. Good morning, everyone, and welcome to our today's presentation on packet trimming. So this feature has been discussed in the SAI and Sonic community, so I'm sure some of you might be familiar with the topic. And in this presentation, we'll touch base on the features, feature design, the functionality, and some of the use cases as well. As we all know, right, every packet loss in the network comes with a cost. So in the world of AI, each packet loss counts. And today in our existing deployments, when the lossy queue exceeds certain threshold, it drops the packet without any notification to the end host. So this packet loss and the recovery is slow. So it will come either with a timeout or a NAC and go back and for retransmission. So packet trimming as a feature is introduced to help in faster notification and retransmission or other actions. So that's essentially the feature capability, and there are like configurations and parameters that are capable of enabling packet trimming in packet trim eligible queues. So the one main thing is like the trim packet traverses the same path as the original because all the headers are retained. So going out to the overview, when the trim eligible queue, like I said, like there are multiple configuration parameters. You can enable the trimming on certain queues, and when drop happens on that queue, that's where the trim action is taken. So when the trim eligible queue is congested, the drop packets are trimmed and enqueued to a different queue. And then with that, I'll hand over to my co-presenter, Kumaresh, who will go through the details of the feature itself. Yeah.
Thanks, Prince. So in the switch, the trim queues are configured with a higher DWRR weight or a strict priority. So this is to make sure that trim packets are given more priority over the other regular data packets. And the trim packets are rewritten with a different DSCP value so that the end host can identify the trim packet just based on the DSCP value and take immediate actions. So other than the DSCP rewrite and changing the packet length and truncating the packet, there is no other additional overhead added to the trim packet. So in case of for any flow, if you want to disable the trim action, so ACLs can be configured to disable the trim action for a flow. So let's take a simple example here. So in the switch, so we have a Q1 as a trim eligible queue, and the trim size is configured as 256 bytes, and the trim DSCP is set to 3, and with the trim queue index as 3. So in this switch, so let's say the Q1 on the egress port is congested. So instead of tail dropping the packet, the switch trims the packet and reduce the packet size to 256 bytes and change the DSCP value and enqueue the packet to Q3. So when we compare the original packet and the trim packet, there's not much difference in the packet header and just the DSCP rewrite from the DSCP 1 of the original packet to DSCP 3 of the trim packet, which is configured 1. And the packet length of the trim packet is reduced to 256 bytes as per the configuration. So in this, so let's say the data packet is around like 4 kilobytes. And whenever there is a trim, which in this case it's a 256 bytes, theoretically, a switch can handle up to like 16 times of the trim packet compared to the original data packet. So next we have packet trimming with asymmetric DSCP. So instead of configuring or instead of setting a single DSCP value for all the trim packets, so the switch sets a TC value, which is the internal priority of the switch, for all the trim packets. So based on the QoS maps that is attached to the final egress port, the final DSCP of the trim packet will be taken. So for example, in this case, so let's say the trim TC value is 8, And we have two egress ports, egress port 1 and egress port 2. And on egress port 1, there is a map which changes the DSCP value from trim TC8 to DSCP 30. And on the egress port 2, we have another DSCP, another TC to DSCP map, which maps the trim TC value 8 to DSCP 40. So based on the congestion and the egress port, the final DSCP value of the trim packet will be changed. So this is mainly useful because in a multi-tier topology, so you could have like T0, T1, T2 uplinks and downlinks. And based on the configuration, the trim packets can have like a different DSCP value. So let's take one use case of the packet trimming, which is a retransmission here. And in our AI backend cluster, we use SRv6. And we have a detailed presentation on SRv6 later in a couple of hours, so please join. So in this case, let's say when the receiver end host receives the trim packet, so that means like there is a congestion happened in the network. So based on the DSCP value received by the NIC, it immediately transmits the trim NAC to the source with the SRv6 segment ID, segment list ID. So once the source receives the trim NAC, it can retransmit the packet immediately using a different path by attaching a different SID list. And as I mentioned earlier, we use asymmetric DSCP to configure different DSCP values across the tiers and also uplink and downlinks. So let's take more detail about the packet trimming use case. So this is our simplified topology of like a backend where we have source and destination GPU NICs are connected across the T0, T1, T2 network. And in this case, let's say there is a congestion between 21T1 and 20T0. So from, let's say the data packets reach 21T1, and here the data packet queue of the link between 21T1 and 20T0 is congested. So instead of dropping the packet, the packet gets trimmed and rewritten with the correct DSCP value that is attached to the egress port between 21T1 and 20T0. And the destination GPU NIC will receives the trim packet with the correct DSCP value that is configured on the 21T1. So immediately after receiving the trim packet, so the destination GPU NIC, it transmits a trim NAC to the source. And here the trim NAC clearly represents that there is an explicit notification of a congested or a drop packet, right? So if you look at it, the destination notifies the source with a trim NAC, and it takes only just one RTT. From the source NIC can retransmit the packet that got lost using a different SID list by attaching the different SID list that excludes the congestion link between 21T1 and 20T0. So this new SID list, which doesn't include the congestion link between the 21T1 and 20T0, can be used for the future data packets. So in this case, the packet retransmission can happen approximately around 1 RTT plus extra overhead compared to any other packet timeout-based approach, which can take like milliseconds or in some cases seconds. So this is the overall packet trimming feature. So now we'll talk about the Sonic architecture, which we use to enable the packet trimming feature. So as we all know, Sonic has like a config DB, application DB to process all the configurations. So here we added a new config, which is like a switch trimming object, which kind of like it takes all the global trimming related configurations. So all the trim TC, trim packet size, as well as the trim queue are configured in the switch trimming object. So we have corresponding switch arc agent, which listens to all the updates of the switch trimming object and calls the appropriate SAI CRUD APIs to program ASIC via SyncD. So next is how to enable the trimming on the queues. So we use the existing buffer profiles. So buffer profile is a template which is used to attach to all the queues. And the buffer profile currently has the threshold, packet size, the min packet size, as well as like dynamic threshold alpha. So in addition to all these parameters, we also added a new attribute for the trim action. And this buffer profile will be listened by the buffer manager D, which kind of parses all the object attributes and pushes the updates to application DB. And there is a buffer arc agent, which kind of like listens to all the updates in the buffer profile and call the corresponding SAI APIs to program the trim eligible queue and also enable all the trim related configurations. So in addition to all these configurations, we also have the flex counter poll, which kind of like constantly polls the SyncD for all the port and queue related trim counters. So for example, if you want to disable the trim action on a certain flow, we have the ACL, and any action that is updated in the ACL rule, the ACL arc agent listens to those updates and takes action by calling the appropriate SAI APIs. So next we'll talk about set of SAI attributes that got added for adding this packet trimming feature, because SAI attributes are the building blocks of the Sonic. So in the existing SAI switch object, we added trim size to configure the trim packet size, the trim DSCP value or the trim TC value based on whether we are using symmetric DSCP or asymmetric DSCP for the packet trimming. And there is a trim queue index. So these are all like a global configuration, which is used for the packet trimming. And we added the buffer profile admission fail action attribute to enable trim or drop action that can be attached to a queue. So these are all the configurations. And all the queue trim related counters, there are like separate attributes that got added. And for ACL action, so there is a new ACL action got added, which is to disable trimming. And yeah, so these are the SAI attributes.
Thanks, Kumaresh.
Yeah.
So again, thanks to the OCP SAI community for helping enabling all these trim capabilities and the attributes. So currently we are looking for contributions from the community for Sonic and even any gaps in the SAI APIs, like extending the counters or some features that you see as like not enabled yet on the packet trimming feature. Now, the plan for the feature itself is to be onboarded to the 2025-11 version, which is the next upcoming version for Sonic. And we also have some of the design HLDs that is posted in the links here. So feel free to take a look. And if you have any questions or on use cases or how we are deploying this, we can take it offline as well. Yeah.
Yeah.
Thank you, everyone.
Thank you.
Thanks a lot, Prince and Kumaresh. Please line up for any questions on both sides.
Thank you for sharing which release it's going to be in, but which community SAI will support it at that time? Which community SAI will support it at that time?
I think the latest SAI release, it has all the attributes.
I mean,
I think it's the
from
one.
which ASIC vendor?
Oh.
Yeah, which will be available in community, in others we can actually use.
The ASIC vendor, I think currently the latest versions of Broadcom, TH5, and also like a Spectrum switches.
NVIDIA, yeah.
And those are available in community?
Yeah.
Yes.
Yeah.
Okay. The other thing is for the retransmit, the trim NAC, is that also, I noticed you guys do SRv6, but in non-SRv6 networks, are those expected also to be prioritized, to speed it up? The NACs themselves?
So yeah, so the trim NACs are also comes with a different DSCP value.
Yeah.
So it can be configured in a certain queues.
Right,
Yeah,
okay. In terms of the implementation, you said the NACs are handled by the NIC, right?
Yep.
Are there commercial NICs available that do this already?
Yeah. There are NICs
From
available.
multiple, like
Yeah.
Broadcom and
Multiple
NVIDIA
vendors,
and
yes.
so
Yeah.
on. Okay.
Yeah.
All right. Thank you.
Yeah, thanks.
Hi. There was an approach presented yesterday where the switch was generating CNP packets. Do you have some thoughts on packet trimming versus that approach, when to use which one?
So the packet trimming is mainly used for the actual drop, right? So the CNP packets are mainly for the congestion notification. So we kind of like have both the WRED to generate the CNP as well as the packet trimming.
Thanks.
Thanks, Prince and Kumaresh. I want to just understand more about the asymmetric DSCP use case. Is the idea that we'll use the DSCP value to understand whether the congestion happened at the TOR or which layer of the network? Is that the idea, to get the DSCP value to identify at what layer the congestion happened?
Yeah.
Okay. Just because there's no way we can, if it's a back to center mechanism like the CNP, you will have the switch ID or something encoded in the metadata.
Yeah.
But here we don't have any metadata, and that's the reason we have come up with intelligent ways to use DSCP.
Yeah. So because we are kind of like trying to push the NIC side to just use the DSCP value to determine whether it's a trim packet or like a regular data packet.
Yes.
Right? So in this case, when you have like a different DSCP values, then the receiver NIC can identify which layer, because even you can have like a T0, T1 uplink or downlink can have like a different DSCP values.
Okay.
And because since we are using SRv6, and it can be used based on the SID list and the DSCP value to determine the correct congestion link.
Okay. Thank you. Thanks.
Yeah, I think that may have been part of my question, but when you do the NAC, do you communicate any telemetry to help indicate what route to choose for the next retry, or is it just up to the NIC? And
It's all up to the NIC. Yeah.
Okay, so just random choice or something?
Yeah.
Okay.
So because the NIC maintains the whole bunch of like SID list, and it will choose.
So it can choose a new route, but it doesn't have any a priori, no telemetry is communicated back to help it choose in your NAC flow. Okay.
Yeah, the trim NAC has the ID which is the SID list ID used by the original data packet, so it can identify the congestion link.
It can identify a congested link, but not suggestions
no suggestion from the receiver. Yeah.
Okay, got it.
Yeah, in extension to that question, how do you avoid NACs getting lost in the network? What if it hits a path that's congested?
Yeah, so all the trim NACs comes with a different DSCP. So in all the switches, it will be prioritized, but I mean, the drops cannot be avoided in all the cases, right? So yeah, in case of drop, there'll be like a algorithm will kind of determine what is the backup plan and determine the and use for the retransmission.
I think that will be the fallback of timeouts and the original like NAC with go back and retransmission. Yeah. All right. Yeah.
Thanks a lot, Kumaresh and Prince.
Thank you.
Thank you.